Let us do an example to find the reflection coefficient given a certain load impedance using the Smith chart. Okay, so let's suppose that we have a transmission line with an impedance Z0 which is equal to 100 ohms, and let's say that ZL is equal to 100 plus J 100. So the first thing that we have to do is to divide ZL by Z0. So ZL divided by Z0 will be equal to 100 plus J times 100, and we divide this by 100, which gives us 1 plus J. So this is the normalized impedance. So let me write it down here. Normalized impedance. Okay, so this is the first step. So we're trying to find the reflection coefficient gamma. Okay, so now how do we do that? Remember that I'm not sure if I mentioned this before, but on the Smith chart, all these circles here, if you see there's a big circle on the outside here, there's also lots of smaller circles inside. For example, there is this circle here at this position where it says 1. This is this horizontal axis here is the real axis. So where it says 1, then it says 1.2, 1.4, 1.6, etc. What this means is that the normalized resistance has the value which is shown here on this horizontal axis. So if you look here where it says 1.2, this means that along this circle here, this big circle, can't draw it well, but you get the idea. Along that circle, the normalized resistance is always equal to 1. And the same thing, for example, if you go to this where it says, this one here where it says 3, that will mean that the normalized resistance anywhere on that circle will be equal to 3. Now the other thing is all these semicircles here that are going up, for example this one, and also the ones that are going down, they correspond to the imaginary part of the normalized impedance, so the reactance. And along the ones on the top are for positive reactance, and the ones on the bottom are for negative reactance. So if we want to find the reflection coefficient on this line at the load, we have to we have to draw a point that corresponds to the normalized impedance. So remember that the normalized impedance that we found was 1 plus J, which is just 1 plus 1 times J. So this is the resistance and this is the reactance. So we look here on the chart, we find the circle which has a 1 written next to it, which is this one, and you mark it like that. And then we do the same thing for the reactance. We look for one of these arcs that has the number 1 on it. The number 1 is right here at the top. And so we mark it down like this. And where the two of them intersect, that is going to be our point. This is going to be the reflection coefficient. And now to find the reflection coefficient here on this chart is represented with polar coordinates. The center here where it says 1 is actually the 0 point for the reflection coefficient. So first we draw a line, straight line from here up to the point. That is going to be the absolute value of the reflection coefficient. And then we find the angle that this line makes with the horizontal axis here. So this is theta. And to find this angle, all we have to do is to continue this line, the straight line from here up to the end here, because at the end we can see the angle. So these values here, 60, 50, 90, etc. Here you have 0, here is the angle. So for this one, this angle So we have 62, 64, 66. This is 67. The angle here is 67 degrees. So the reflection coefficients then, so then what we have to do is to find the length. You take a ruler and you find the length of this line here. Let's say the length is equal to 3 centimeters. So now the absolute value is not going to be 3 centimeters. We have to take into account the length of this chart here. This whole length here, the radius of this chart, because this chart has an arbitrary size. It could be a huge chart, it could be a very small chart. So we divide the 3 by the radius of this chart, which in this case is 8 centimeters. So we have 3 over 8 centimeters, and that's going to be 0.375, 0.375, and this here is the actual absolute value of the reflection coefficient. So we have found the reflection coefficient very easily like that, which is 0.375 with an angle of 67 degrees. Okay, so now we can convert this into a Cartesian complex form, which is equal to 0.375 times e to the j times 67 degrees. Now 67 degrees, we need to convert that into radians. So in order to do that, we do 67 divided by 360, and we multiply that by 2 pi. So this is 1.16. So the result is 0.375 e to the j 1.16. Now this is also equal to 0.375 times cosine of 1.16 plus j sine of 1.16 using Euler's formula. So if we calculate that right now, cosine is 0.39. 0.39 times 0.375 is equal to 0.750 plus j times, now we find the sine of 1.16 sine times 0.375, this is 0.34. So this right here is the reflection coefficient that we have found at the load. So as you can see, it's quite easy to calculate. The Smith chart helps you a lot. And just one more thing about the Smith charts before the next tutorial. You have to realize that this chart here has 2 types of coordinates in it. The reflection coefficient is using polar coordinates, with the center here equaling 0, r equals 0, and this axis here is theta equals 0. And this is the imaginary axis, and this is the real axis here. And however, there are also another type of axes here, which are these circles. All these circles here and these semicircles at the top, they are another coordinate system which represents the impedance, the normalized impedance. So also another thing is this length here is the maximum length of the of gamma, the absolute value of gamma, and this is equal to 1. So all around this circle here, we have that the absolute value of gamma is equal to 1. So the absolute value of gamma is equal to 1. Here, on this point here, gamma is exactly equal to -1. On this point here, gamma is exactly equal to +1. At the top here, gamma is exactly equal to plus j, and here gamma is minus j. So as you can see, gamma can be any value you see around this circle here, any value here, and for each value you have an absolute value in a phase of gamma. So this was an example. I hope you have enjoyed this, and I'll see you in the next tutorial.